All right, let's get started here. Let me move this a little bit. That's what I want. Okay, so welcome back from break, and hopefully put the homework off for a few days before starting it. This week's a lot shorter than last week's, and we're actually going to strike an additional problem as well. So there's some announcements on the board. I'll get to them if I have time at the end, but essentially skip number 4 on the recitation homework for this week. So you really only have like 4 problems to do. And okay, so let's talk about what we're doing today. So today we're going to be talking about Jordan canonical form. Oh yeah, right here. Thank you. So what is Jordan canonical form, right? So let's recall diagonalization. Right, A is equal to SDS inverse. And when can we write A is equal to SDS inverse? Well, we have a condition, which was the following. For every, right, for every distinct lambda, the algebraic multiplicity has to be equal to the geometric multiplicity. Right, and if we don't remember what those are, remember algebraic multiplicity was the number of times lambda appears in the characteristic polynomial, and the geometric multiplicity is the dimension of the kernel of A minus lambda I. Thank you. Okay, so remember, so to be able to diagonalize a matrix, we need this condition where the algebraic multiplicity is equal to the geometric multiplicity for every distinct lambda that we have. But that's not always the case, right? It's not always going to work out this well. So the question now is what happens. No, I got it. If A is defective. All right, and so what does defective mean? Defective just means non-diagonalizable. Okay, so what happens when a matrix is defective? Well, for at least one lambda, the algebraic multiplicity is greater than the geometric multiplicity. Okay, so what happens when we have A is defective? Well, the following. We have to write it then in Jordan canonical form. All right, so JCF is Jordan canonical form, and so for a defective matrix, this is how we have to write our matrices. And in Jordan canonical form, you write A as SJ S inverse rather than SDS inverse. Okay? And so what is S and what is J? Well, S is now your matrix of generalized eigenvectors, and J is a Jordan block matrix. All right, and so we'll define all of these in a little bit here. Okay, so key word here is the generalized eigenvector, and J is the Jordan block matrix. So you're going to realize that SJS inverse is really similar to SDS inverse in structure and in how we construct it as well. Okay, so let's talk about what Jordan block matrices are. So let's take a look at some examples of Jordan block matrices. All right, so I can have something like 1, 2, 3, 4 on the diagonal. And this is a Jordan block matrix, right? And how? Well, essentially, we have 4 1-by-1 blocks, right, on the diagonal. Okay, so that's an example. What else is an example? Well, if we have something like 2, 2, 2, 2, all right, and then we put the 1 above the diagonal here. Thank you. We have 2 as a block, right? And then we have a 2-by-2 block here that encapsulates that 1, and then we have another 2 down on the right-hand side. All right, so there are 3 blocks there. We have a 1-by-1 block, a 2-by-2 block, and another 1-by-1 block. All right. Lastly, we can have a matrix that looks like this: 0, 0, 0, -3. Okay? And then let's say I have the 1 and the 1 above the zeros there. All right? So now this is a Jordan block, and that's a 3-by-3 Jordan block, and this in the bottom right is a 1-by-1 Jordan block. And so in that matrix, you have 2 blocks. Okay, so this is a Jordan block matrix, and these types of matrices are going to be the ones that go in the middle of SJS inverse. Okay. So now that we've gotten Jordan blocks out of the way, they're the more simple ones, I would say, out of the concepts here. Let's talk about what a generalized eigenvector is. Okay, so generalized eigenvector is the following. It's a vector v such that a minus lambda I raised to some power p times v is equal to the 0 vector. Okay, and in this case, p has to be greater than or equal to 1, and p has to be an integer, right? So that's what p in z means. Z is the set of integers. Okay, so p has to be a positive integer, and v satisfies a minus lambda I to the p is equal to 0. So in particular then, if p equals 1, what do we have? Well, if p equals 1, I have a minus lambda iv is equal to 0. So what is v in this case, in the p equals 1 case? Yeah, it's just a regular eigenvector, right? Because remember, for regular eigenvectors, a minus lambda I times v is equal to 0. Okay, so if in the p equals 1 case, this is a regular eigenvector. Okay, so which leads me into the more general statement then. All eigenvectors are generalized eigenvectors, but the converse is not true, right? Not all generalized eigenvectors are eigenvectors. Right, so it's the same analogy as all squares are rectangles, but not all rectangles are squares. Right? In this case, any eigenvector that you give me satisfies the generalized eigenvector definition, but if p were like greater than 1, then that's not going to be an actual eigenvector. Okay? Or it may not be an actual eigenvector. So that's what generalized eigenvector is. Probably just talking about this like as a definition doesn't make too much sense. So we'll see an example then right here. How do we find generalized eigenvectors? And more importantly, how do we find a cycle of generalized eigenvectors is what we really care, which is what we care about more. Yeah.
Wait, just what does that say? P is an element of
Z. So Z are integers. Yeah. So this is the notation for integers. Yeah.
Oh, was there a formal definition for a Jordan block matrix?
No. I just show examples. So the one thing that you have to see is that the only number we can have above the diagonal is 1. So we don't have like any other number above the diagonal. I guess that's like formally, but that's just how we write it in SJS inverse form. Okay, so that's generalized eigenvector, and let's move on then to an example of finding S and J. So we want to find S and J such that A is equal to Sj S inverse. Okay. So how do we actually write this in Jordan canonical form? So if we let A equal this matrix 4, 1, -1, -1, 2, 1, 1, 1, 3. All right. So step one is to always find the eigenvalues, eigenvectors, or to find the eigenvalues, and I'm just going to give them to you here. It's going to be 3, 3, 3. Okay, so A is equal to that matrix. Lambda is 3, 3, 3. So now we just need to take out the lambda equals 3 case. Right? There's only one case to look at. It's lambda equals to 3. And in this case, right, the algebraic multiplicity is equal to what? It's equal to 3, right? Lambda shows up 3 times in the characteristic polynomial, so the algebraic multiplicity is going to be 3. Right, so now we take a look at A minus 3i. 1, 1, -1, -1, 2, 1, 1, 1, 3. Oh, I did not subtract stuff off the diagonal. -1, -1, 1, 1, 1, 0. Okay, so when we look at A minus lambda I, right, what do we care about? Well, we care about the rank and we care about the nullity of that matrix, right, of A minus lambda I. So in this case, what is the rank of A minus 3i here? It's 2. The first and the second rows are multiples of each other, and they're the only like ones that are the same. And then what's the nullity? Well, the nullity is going to be 1 by the rank nullity theorem, right? And remember, what also is the nullity? The nullity is the geometric multiplicity for that lambda. All right. So from lambda equals 3, the geometric multiplicity is less than the algebraic multiplicity, right? 1 is less than 3, and so we have a defective matrix. Okay? So now how do we find, right? So we know that it's a defective matrix. If we know it's defective and we have this case right here, don't just start and try to find eigenvectors because that's going to be wrong. So what we want to do instead, right, we want to generate eigenvectors using a cycle of generalized eigenvectors. All right, so let's see how we do this. The first step is to just find J. And in this step, we want to determine the size of your Jordan blocks. Okay, so we want to find J. And how do we do that? Well, J is equal to this matrix. All right. And so A is equal to SJS inverse. J is going to be very similar to D in that your eigenvalues are going to be on the diagonal. All right. So in this case, right, what are my eigenvalues? Well, they're 3, 3, 3. All right. So that's the exact same thing as we do for the diagonal matrix case, except now we have to consider the geometric multiplicity here. Okay? And so what does the geometric multiplicity tell me? The geometric multiplicity tells me the geometric multiplicity of lambda equals 3 tells me the number of blocks associated with lambda equals 3. And so in this case, remember geom multiplicity was equal to 1. right, from up here. All right, so what does that mean? That just means that in my J matrix, right, for my lambda equals 3, I have one Jordan block that encapsulates all of the lambda equals 3s. All right, so that means for a 3 by 3 matrix, there's one block, and it's the entire matrix. There's a 3 by 3 block. Okay? And so now, how do I fill in J? Well, if we go up here, right, and we look at this 3 by 3 block, right, you just put 1 above the diagonal. All right, and so that's how we finish our J matrix. So now we go in, and we put that 1 in, and now we put that 1 in there. Okay, and so that's going to be our Jordan matrix. And that's going to be the J in the middle of SJS inverse. Okay? Any questions on finding J? All right, it's like D, it's not the worst. Okay, so now for the second step, you need to find your cycle for each block. And so now we go to our S matrix. And so what happens is the following. This block, right, I have one 3 by 3 block. That means down here I'm going to have a 3 cycle. Of generalized eigenvectors. And it's going to look like the following. So in the third column, I'm going to have a vector. I'm going to name it VG as it's one of the generalized eigenvectors that I find. Okay? And we're going to have conditions on how to find VG in a little bit here. But this is just what a cycle is, right? So since this is a 3 by 3 block, I have a 3 cycle. All right? The second column is A minus lambda I times VG. And then this first column is A minus lambda I squared times VG. All right? And so you can kind of see why it's a 3 cycle, because VG appears 3 times in this cycle. Okay? So that's why we call it a 3 cycle. All right? And the idea holds, right? If this were a 4 by 4 block, you would just have to go out to A plus minus lambda I cubed times VG, right? You just need to continue increasing the power for a 4 by 4 block. If you had a 2 by 2 block, you wouldn't have to have that first column there. Okay? So now that we've introduced all this notation, right, how do I find VG? So finding VG is the following way. So you want to raise A minus lambda I to the power of the size of the block. So what do I mean by that? Well, the block is a 3 by 3 matrix, right? The block is a 3 by 3 block, so I need to raise A minus 3I to the third power. Okay? So in our case, right, A minus 3I was equal to 1, 1, negative 1, negative 1, negative 1, 1, 1, 1, 0. Okay, and so now I need to raise it to the third power, because that's the size of my block. So A minus 3I squared is going to be negative 1, negative 1, 0, 1, 1, 0, 0, 0, 0. Okay, so that's just multiplying A minus 3I by itself, and this is the result that you get. And then A minus 3I cubed is equal to just the 0 matrix, and we're not going to write out all of the entries there. Okay, so that's the first step. Okay, so what do you do after you raised A minus lambda I to the size of your block? Well, VG needs to satisfy some conditions. All right, and especially the following conditions. we need a minus 3i cubed times vg is equal to 0. A minus 3i squared vg to not be the 0 vector. And then a minus 3i vg cannot be the 0 vector as well. And for these last two cases, can anyone see why that has to hold? Why can't we have a minus 3i squared vg not be... what happens if any of one of those two are the 0 vector? Right, exactly, right? So these two vectors right here, if we go up, right, we kind of plug them in into the first two columns there, right, into the S matrix. But what are we trying to do with the S matrix? SJS inverse. So we have to invert the S matrix, right? Well, what happens if you have a 0 vector in a matrix? Can you invert it? No, right? Because the 0 vector automatically makes the determinant of that matrix 0, and so the determinant's not invertible, and so the matrix is not invertible. So that's why these two conditions have to be satisfied, and the first condition also has to be satisfied as well, because that's just how we choose the vector that starts our cycle. Okay? So in this case, right, what should VG be? Any ideas? So here are my three matrices that I are really concerned about, and I need this generalized eigenvector to satisfy these three conditions here. Okay? Well, if we look at what a minus 3i cubed is, it's the 0 matrix, right? And a minus 3i cubed times vg has to be a 0 vector. Literally any vector works, right? Because I'm having the 0 matrix times some vector, right? And that's always going to be the 0 vector. So almost any vector works. And so don't get too creative here with the vector you choose. Just choose the simplest one that works, right? So in this example, right, what doesn't work? Well, 0, 0, 1 doesn't work, right? Why does 0, 0, 1 not work?
A minus I squared.
Yeah, so it fails the second condition here, right? Where if I multiply this matrix by 0, 0, 1, that would be 0, 0, 0, and that's bad. Okay, so we can't use 0, 0, 1, but we can stick to this theme of just having one entry be non-zero. Instead, let's choose VG to be 1, 0, 0 instead. Okay, I'm just completely picking it arbitrarily, because why? Well, here's a minus 3i cubed times 1, 0, 0, and that's the 0 vector. Okay, so that's satisfied. Now if I multiply a minus 3i squared times 1, 0, 0, that's going to be negative 1, 1, 0. Okay, and that's not the 0 vector, which is good. And then lastly, we multiply a minus 3i times 1, 0, 0, and we get 1, negative 1, 1, which is also good because that's not the 0 vector. Okay, so 1, 0, 0 satisfies our condition. And here we generate the other vectors. So what do we do? After we've multiplied all these out, we see that 1, 0, 0 gives us a 3 cycle. We go back up to our matrix here, right, and we plug it into our S matrix. So what do we choose for VG? We chose 1, 0, 0. Okay, so 1, 0, 0 goes in the last column. All right, what goes in the second column? Well, the second column has a minus lambda I VG, which is this entry up here, the first one. And here it's 1, negative 1, 1. And then finally, the first column is a minus lambda I squared VG, all right, which is negative 1, 1, 0. It's the second calculation that we did here. All right, and there we go. That's our S matrix. So we had 1 3 cycle in our S matrix, and we found it by raising a minus lambda I to the third power. Okay. Any questions? So for those of you that came in late, all this might seem new, and it is new because yesterday, so essentially what we're covering now is what's going to be, what I'm covering now is going to be covered on Thursday, tomorrow. And so this stuff is very, like, it's just very formulaic. There's really, like, we don't have the tools necessary to develop, like, intuition or, like, theory behind it. We kind of just have to, like, present it as just do this, which is kind of unfortunate given how, like, interconnected everything else is before the Jordan form stuff. But it's on the syllabus, so, like, we have to do it. Okay, so that's how we do, so that's my S matrix. So one thing you notice is that there are, like, infinite numbers of VGs that I could have chosen. Right? I could have picked 0, 1, 0, and then I could have generated a cycle using 0, 1, 0 as well. Okay? It doesn't matter. It would have given me the same answer because at the end, when you calculate Sj, S inverse, you'll just end up with the original matrix, even though you chose a different generalized eigenvector to start off with. Okay? What else do I want to say here? Yeah, one more thing. If we notice, what is this vector here? Can anyone tell? So this first vector is an actual eigenvector. It's not a generalized one, right? So if we look at a minus 3i, or if we want to go up here, right, a minus 3i, and we consider negative 1, 1, 0, right, and we do the dot product, you get 0, 0, 0. Okay, so in this process of creating a cycle of generalized eigenvectors, we actually generate the eigenvector that we want. All right, and so this guy is the actual eigenvector. And in general, right, this first, the leading vector of a cycle is an actual eigenvector. All right, the others, these other two must be generalized eigenvectors. Okay? And so this is why we don't just look for eigenvectors immediately when we calculate a minus lambda I. It's because we actually have to generate that eigenvector from the generalized ones. If you found like the actual eigenvector first, you kind of have to work backwards to find your generalized eigenvectors, which isn't very ideal. Okay, so that's an example. So let's take a look at another example just to concretize the ideas. So let's say we have A is equal to 0, 0, negative 1, 3, 0, negative 5, 4, 0, negative 4. Okay? And we're going to do the same thing. Find Sj such that A is equal to Sj S inverse. And here, the eigenvalues are negative 2, and 0. All right, so it's a little bit different from before in that we don't have the same eigenvalue that's repeated 3 times, but rather we have 2 distinct eigenvalues. Okay? So what do we want to do? Well, is the 0 going to give us any problems? No. Okay? And why can't the 0 give us any problems? Well, if we know it's an eigenvalue, right, the algebraic multiplicity is 1, but if the algebraic multiplicity is 1, then the geometric multiplicity has to be 1, right? Otherwise, it's just not an eigenvalue. So, yeah, and in general, right, what's going to give us problems are the repeated eigenvalues, right? So whenever you see repeated eigenvalues, like alarm bells should go off in your head, and you should be like, oh, hey, something might be wrong. We might have a defective matrix when we have repeated eigenvalues. Okay, so because we have this lambda equals 0, and we know that it's not going to give us any trouble, we're going to start off looking at lambda equals 0 first. So, well, what is lambda equals 0? It's a minus 0I, so it's just a. Okay? So we just look at A and we try to find an eigenvector for A, and we come up with 0, 1, 0. Okay, are we okay with that? So for lambda equals 0, we just get V is equal to 0, 1, 0. All right, and this is because A minus 0, I is equal to A, and then so we don't have to rewrite the matrix. All right, lambda equals negative 2. So now here's where we note that this has algebraic multiplicity equal to 2. Right, it's repeated twice. And now we look at A plus 2I, which is 2, 0, negative 1, 3, 2, negative 5, and 4, 0, negative 2. Okay, so what's the rank of this matrix? Two. And that means the nullity is 1, right, which is equal to the geometric multiplicity. And so we have the case where the geometric multiplicity is less than the algebraic multiplicity, so we have a defective matrix. Okay. So remember, how do we find S and J? Well, the first step is always to find J, because it's not that bad. So what we do first is we're going to put our eigenvalues on the diagonal, right, which are 0, negative 2, negative 2. All right? So here's the thing. You know that the negative 2's have a block. Okay? So you can't put the zeros in between the negative 2's. All right, but you can put the 0 wherever you want. So I could have this, or I could have 0 on the bottom and have negative 2's up here. It doesn't matter. All right, as long as the negative 2's stay by each other and the 0's by itself, we're fine. So let's just go back to what I had originally. Right, we're just gonna have the negative 2's on the bottom. Okay, no particular reason. So 0, right? We don't have to worry about it. It just stays on the diagonal, right? It's just the eigenvalue. It's not repeated. There's one block associated with it, and it's just itself, right? Because remember, if you look at the examples of Jordan block matrices, you can just have that diagonal entry be a block. Okay, so now what? Well, for lambda equals negative 2, right, the geometric multiplicity is equal to 1. So how many blocks do we have associated with lambda equals negative 2? You have one block, right? So for lambda equals negative 2, geometric multiplicity is 1, so the negative 2's just get swallowed up by one block. Okay, and now to fill in the block, we need to put a 1 above the diagonal. Okay, everything good so far? All right, so now, right, we want to find the cycles, and we want to put them in S. So here's the thing: with 0, right, it's just the eigenvalue by itself, so we don't have to worry about any generalized eigenvalues. Okay, so S is going to be the exact same thing as in diagonalization, where we just match up the eigenvector with 0, and we just put that in the first column. All right? So there's no cycles needed for lambda equals 0. And so our eigenvector is 0, 1, 0, and that just goes straight in the first column, matching that lambda equals 0. Okay, but now in the second and third columns, we need a cycle, right? We need a 2 cycle for this block. And so what is the 2 cycle going to be? Well, we put VG at the end, right? And now we have A plus 2I VG as the second column of our matrix. All right? Or the leading column of the cycle. All right, so now we have to find VG. And remember, how do we find VG? Well, we raise a minus lambda I to the power of our block, right? So in this case, our block is a 2 by 2 block. And so I want to find a plus 2I, which was 2, 0, negative 1, 3, 2, negative 5, 4, 0, negative 2. And then since it's a 2 cycle, it's a 2 by 2 block, a plus 2I squared is the highest power I need to find. And you'll get 0, 0, 0, negative 8, 4, negative 3, 0, 0, 0. Okay, so find VG, right? The block is 2 by 2. So a plus 2I squared is the highest power. All right, remember the conditions that this needs to satisfy, right? We need to satisfy that the highest power times VG is 0. So this needs to satisfy a plus 2I squared VG is 0, but a plus 2I times VG is not the 0 vector. Okay? And so now we need to pick a VG that satisfies all of this. All right, so we look at the kernel of a plus 2I squared, and we need to pick a vector there. Any ideas? 1, 0, 1 for a plus 2I squared? Oh, okay, so not quite. You don't want to look at the columns, you need to look at the rows. Yeah. Yeah, someone just said it, right? 1, 2, 0. Okay? So, yeah, 1, 2, 0 is the generalized eigenvector that we want. All right, what doesn't work? So 2, 7, 4 is actually in there as well. Okay? If you looked hard enough at a plus 2I squared, you would have come up with 2, 7, 4 at some point. This is wrong. All right? Why is it wrong? Well, because if we multiply this by 2, 7, 4, it's 0. Okay? So, and in fact, 2, 7, 4 is the eigenvector that we're going to generate. So when we plug in 1, 2, 0 here, that's equal to 0, that's equal to 0, 0, 0, which is good. And now if we plug in 1, 2, 0 into a plus 2I, we get 2, 7, 4. All right, and this is a plus 2I times VG. Okay, so now we go back up to the S matrix, and we can fill in our cycle. So that's still 0, 1, 0. A plus 2I VG was 2, 7, 4. And remember, this is an actual eigenvector. And then the last thing we need to put in is VG, which we picked to be 1, 2, 0. Okay, and so that's S, and we found J, which is up there, and so we're done. Any questions? Yeah.
Is the rest of the J vector like 0?
Yeah, everything else is 0. It's like the D matrix. We really care about like the blocks on the diagonal, essentially. So yeah, everything else is 0 there. Okay. Yeah.
The first eigenvector is also an actual one, right?
Yeah, so that one was straight up for lambda equals 0, right? So if you actually had the case, let's say this 0 was a negative 2, right? So now this is all negative 2s, all right? We actually can't go hunting for this first eigenvector. Because if this were a negative 2, plug for my Friday review session that I'm going to hold this week. It's on the board. I'm going to talk about like the case when this happens there. I'm not going to get to it today. But essentially, you need to generate the correct eigenvector first, and then you need to go look for the other linearly independent one. Because the nullity is going to be 2, because there's going to be 2 Jordan blocks associated with lambda equals -2 at that point, right? So one of them is going to be the generated eigenvector, and the other one is going to be the linearly independent one that you have to hunt down by yourself. Okay? But you always want to deal with the cycle, or you always want to deal with your blocks first before you go find linearly independent eigenvectors if they are all the same eigenvalue. If they're different, then they're in different eigenspaces, right? This one's in the eigenspace for 0. These are in the eigenspace for -2. So then you can go do them separately. But if they're the same eigenspace, then you kind of want to deal with the blocks first. But again, not going to really get to that today. There's one other important thing that I want to get to. All right. So any other questions? All right. So last example is the following. So I want to find an example. Find J such that, find J, and we're given that A is equal to this matrix. It's a bit big. -3, -3, -3, -3, -3, 1, 2, 3, 4, 3, 2, 1. All right, and then everything else is 0. Okay, so find J given this matrix. What are the eigenvalues of this matrix? Yeah, -3. And what's the multiplicity? Yeah, algebraic multiplicity 5. Right? So for a triangular matrix, lambdas are the diagonal values. Okay, and that's just simply because if you take the determinant of A minus lambda I, you get a diagonal matrix still, so you just multiply the diagonal terms. Okay, so lambda equals -3 is algebraic multiplicity 5, so lambda equals -3, right? And we get a plus 3i, which is 0, 0, 0, 0, 0, 1, 2, 3, 4, 3, 2, 1. Okay, what's the rank of A plus 3i? Not quite. Two. Okay, and that's because these rows are the same, but the row of 0, 1, 2, 3, 4 is different from the rest. Okay, so the rank is equal to 2. All right, and then by rank nullity theorem, nullity is equal to 3, which is equal to the geometric multiplicity. So geometric multiplicity is less than the algebraic multiplicity, right? So it's defective. So okay, so we need our J block, and this entire example, right? We're just trying to find J by itself. Okay, so J, right? First of all, we're just going to put -3 on the diagonal. All right, but given that nullity is equal to 3, the geometric multiplicity, right, is equal to 3. That's equal to the number of blocks for lambda equals -3, right? So I have 3 Jordan blocks corresponding to lambda equals -3. And that, again, comes from the geometric multiplicity, which is the nullity. What's the problem with that? Yeah.
There's like more than one way to split them.
Yeah, there's more than one way to split up the blocks. So that's very not ideal. So the key question here then is how to split up the blocks. Okay, and there's how many ways can do it? Well, there's really only two ways. So the first way is if you have 2 by 2, 2 by 2, 1 by 1. And the second way is 3 by 3, 1 by 1, 1 by 1. Right? And the reason why these are the only two ways is because if you rearrange them any other way, you're not changing the size of the blocks. You're just moving where the blocks are. Right? And remember, with that previous example, I was like, you could put the 0 wherever the heck you wanted to, as long as you didn't split up the 2's. Right? So it's the same idea here. You're going to have the same number. You're going to have the same size blocks. It doesn't matter where they are, as long as like the sizes are the same. All right? So these are the only two possible ways to do it. Okay, so now the idea is, how in the world do we figure out which one is which? Okay, and this is what we want to do. So there's really no good way to do it. You just have to like guess one of them and hope it works. So assume that it's a 2-2-1 split. All right. So what do I need to do? Well, what's the power of my blocks? Well, the highest power is 2. Right? So here's a plus 3i, which was 0, 0, 0, 0, 0, 1, 2, 3, 4, 3, 2, 1. All right. And then a plus 3i squared, right, which is the power of my highest block, or the block of interest, is going to be 0. Actually, it's just 10 in the upper right-hand corner. Okay, so if we assume a 2-2-1 split, right, the power associated with each block is 2, 2, and 1. All right, so the highest power I ever have to raise it to is lambda equals 2. All right, it is the second power. So what do I want now? Well, remember, so since I have two blocks of size 2, I need to find VG1 and VG2 linearly independent. Okay? And they need to satisfy a plus 3i squared, Vg is equal to 0, and a plus 3i Vg is not equal to 0. Okay, so what are my possible VGs? One zero zero doesn't work. Why doesn't that work?
Oh, because the top one.
Yeah, 1 0 0 kills the top matrix, right? So that doesn't work. But if we keep moving that 1 over, right, that works. So 0 1 0 0 0, right? 0 0 1 0 0, 0 0 0 0 0 0 1 0 0, and then what about 1 at the bottom? That one doesn't work. Why not? Yeah, you get the 10 if you have 0 0 0 0 1. This one doesn't work because the 10 pops out. All right? So we can't do that. So these are our three possible VGs. And any other VG that you come up with is going to be a linear combination of these three. All right? So I'm just going to say that right now. So these are the possible VGs that you can pick from. Or the easy VGs you can pick from. So if I let VG1, so let VG1 equals 0, 1, 0, 0, 0, right? A minus a plus 3i times VG1 is equal to what? Well, it's this times 0, 1, 0, 0, 0, which is going to be just the second column, right? Because the 1 is in the second column here. So 1, 0, 0, 0, 0. Okay, so that's equal to 1, 0, 0, 0, 0. Okay, and now if I let VG2 equal 0, 0, 1, 0, 0, what is a plus 3i times VG2? Well, you go up to that matrix, right, and you just replace it with that. And what do you get? Well, now you get the second column. 2, 0, 0, 0, 0. What's the problem there? They're not linearly independent. These two vectors are not linearly independent. Right? Why is that a problem? Why do these vectors have to be linearly independent? Well, these were linearly independent, right? So why is the bottom ones being not linearly independent? Why does that create a problem? Where do these vectors end up? In S. And what do we do with S? We invert S, right? So they have to be linearly independent, okay? So, all right, I mean, we had 3 possible choices. So if we let, I guess, so this doesn't work, right? So now if we let VG2 equal 0, 0, 0, 1, 0, right? What do we get when we do A times plus 3I times VG2? Well, we kind of don't solve that problem either, because now we get 3, 0, 0, 0, 0. Okay? So you get 3, 0, 0, 0, 0, but that's still not linearly independent from 1, 0, 0, 0, 0. Okay? So what does that show us? That shows us that we can't have two cycles. Right? We can't have 2 by 2 blocks, because we're not going to end up with enough linearly independent vectors that are generated by them. All right? So this shows that we cannot have 2 by 2 blocks. All right? So if we go back up to our possible blocks, this can't be the split. All right? So our blocks must be split up into 3 by 3 and 2 1 by 1s. Okay, so if we look at what J is going to be, that means we're going to have a 3 by 3 block and then 2 1 by 1 blocks. And that's the only way we can split up this matrix. All right? And the reason why we can't have 2 by 2 blocks is because we are not able to generate linearly independent eigenvectors for both blocks. All right? Okay, so announcements. No regular homework due next week. Right, that's pushed back. It's due the day after the midterm now, and all that stuff's going to be on the midterm. In fact, you can do a lot of what's on that homework already, just from this recitation alone. Recitation homework 9 up here. Skip number 4. So it's only going to be 4 problems this week. So we toned it down after the spring break one. And then weekly review session, I'm going to hold this on Friday again. Room is to be announced. You can just show up at whatever one you want. It's going to be at 10 to 11 and 11 to 12. And what I'm going to talk about, I have a lot of topics in the eigenvector and eigenvalue stuff that I want to talk about. A lot of it including the relationship between null space, eigenspace, and column space. So stuff like that, I think it's really important. It's more of an extra topic. But it's a key conceptual idea to have an understanding of. So yeah, those are the 3 announcements. And again, skip number 4 on the recitation homework for this week.
Do we not have recitation number 8?
It's the true false on the back.
Oh, okay.
Yeah, that was 8. Do you have one? Yeah, and grab one if you don't have one ready.
So to do the 26th then and not the 19th?
So the lecture homework is due after the exam. Yeah. So the
day after?
Yeah, the day after. Yeah. And then the recitation homework is still due next week, but it's shorter. And skip number 4. Yeah.
Just to finish up this one, if we look at the vector structure, so the final S matrix would be once you found the 1 VG, this
Right.
you find eigenvector A times lambda I equals 3G,
Right.
VG, and then the other 2 eigenvectors, right?
Exactly. So you'll have 1 3 cycle, right? You have one of the eigenvectors generated from the 3 cycle, and then you have to eyeball the kernel for the other 2.
Do you know when I can pick up my homework?
Yeah, well, you can do it right now, actually, if you have time right now.
Yeah.
Okay.